welcome to this video. We're going to look at the abalone dataset. It's found on, oh, there's an internal error. Maybe we can find it here. It's on, it's the UC, is that UCI or UC? Yeah, UCI, machine learning repository. All right, this is giving me a bit of trouble. Maybe we can search it here. Oh, there we go. Right, so abalone datasets predict the age of, is it abalone or abalone? I'm not sure. I'm going to say abalone. But we're going to predict the age of abalone from physical measurements. Now, I don't know much about abalones, but I do know a little bit about machine learning. So I'm going to apply, well, I already have applied, but I'm going to talk you through it. A simple machine learning deep learning model, or multiple models to this, and see if we can predict the age of abalones from physical measurements using this. It's going to be a gradient descent algorithm, which is one of the simplest deep learning models. So this tutorial here is going to be a introduction to how to use or how to code up a PyTorch gradient descent algorithm. So if you don't know much about that, then this is good. It's good for beginners, but it's going to be a real world, well, a moderately real world example. Now there is a spoiler: we don't really predict it very well because it's such a simple model that we use, but we do our best. Okay, so you can find the data set here. You can download it here. If you download it, it comes up with this. Wait, not this, in data. So we get the names, index, and data. The data here, this is what we want. That's what we're going to put into Google Colab. And essentially it tells you the, and will tell you the sex. So either male, female, or infant. That's the description for that. And then we have the length, diameter, height, weights. And the target variable is the number of rings. So it explains here that it's difficult to predict. What is it? It's time-consuming task to predict the age of abalones through the traditional method, which is cutting the shell through the cone, staining it, and counting the number of rings through the microscope. But if we find a method to predict the age through other variables regarding the abalones, then, well, that'll be a lot more efficient. Anyways, so we've got a Google Colab notebook running, and I'll just call this YouTube abalone. Yeah, so essentially we're going to just apply, I'm going to talk you through it as I code it. We're going to apply PyTorch, just simple models, deep learning models to the data. So we want to just import a variety of libraries first. So we're going to work with data frames. So we import pandas. We're going to work with NumPy as well, with arrays, NP, and we'll import Seaborn as well. That's going to be the plotting, and same as matplotlib. PyPlot, there you go, as PLC. So, and of course we need to import Torch, and then there's another library we need to import, or we need to import from Torch, we need to import NN, and that's going to be a something that we use quite often. And as well as that, we've got train test split, which is going to split our data into training and testing samples, and I'll explain that more later on. And that is all we need so far. So we run that. while that goes, I'm just gonna copy some data over. So we're gonna copy the abalone data here, and that's how we're gonna get the data into Google Colab. All I did was just drag and drop data. But the thing is that the data there, it disappears after you close the page. So make sure it's saved somewhere else. Now we're going to load in the data set. So let me just write this down here. What is it? Insert text cell. There we go. Loading in the data set. And well, that's just a matter of creating a data frame and storing in the data into that data frame. And we've got the data here. It's abalone.data. So we use pandas, and it's a CSV file. So we just read in abalone.data. If it was a Excel file, I think it's just read Excel. And I'm not sure if there's any other types of files out there, but those are the most common ones anyway. So CSV is just comma separated values. So once we've got this, well, we just need to type in header equals none. I'm not going to do this now, but when you get the data, all you need to do is just open up the data and see what format it's in. And if it has a header, then you don't have to do the header equals none section, but if it doesn't have a header, which is just the top row, then you put header equals none. And in that case, it'll load in properly. Otherwise, for example, if you don't have a header, but you don't specify in this code, then it might skip the first row and put that as a header instead. But this is just well, just simple logistical issues. If you just look at the well, really, if you just try it out and then it doesn't work properly, you can kind of go back from there and see, okay, well, the first row is positioning it as a header. So then I'd look into the documentation of read CSV and see if there's anything that could fix that. Or you could literally just put it into ChatGPT and that'll tell you the problem. Okay, so we'll load in the data set and look at what it is. So there we go. So this is the first row. And well, for example, if I removed this thing, what would happen is the first row would be as the column titles instead. That's what I mean by the header. So that's what would happen. Anyways, yeah, so we've got this. We don't have any column titles though, because in the data set, in the data file, there's no specification for the column names, but that's fine because we've got it on this page here. We can put it there. But before we do that, we're just going to, this is a habit that I like to do. It's to create a copy of the original raw data frame here, and that's because sometimes it just takes a long time to load in the data. In this case, it doesn't, so it's not necessary, but it's just, I find that it's a good habit to do that, and then you can just comment this out. And if you need to get the original data frame for any reason, then you can just create another copy from df raw. So we're going to work with df instead of df raw. So now we're going to pre-process in the data. So this was a short section here. So the next section is exploratory data analysis and pre-processing. So we're going to pre-process the data into something that we can feed into firstly something that we can understand, which is going to be to create the column names. And then we're going to make it into something that we can put into a neural network, which is ultimately what we want to do with PyTorch. If we move this downwards, there we go. So firstly, we're going to create the columns, and that's just really as simple as just copying the column names from here. So we have the variables table here. So the first column is going to be sex, and it's going to be length, diameter, and all that. And if we look at df, we can see anyways that that's what it is. So the first column is m, f, and I. Obviously that's sex, and the last column is integers, whole integers values here. So it looks like it's going to be the rings, potentially. Well, hang on, 1, 2, 3, 4, 5, 6, 7, 8, 9. I didn't have to count that out. I could have figured that out just in my head. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so rings is included there. And that's the target variable there. Oh, okay, so then here, this was what I was wondering, because there's no column for age, which is what we want to predict. But if we predict the rings, we can just predict the age, because there's 1.5 plus years after the number of rings. So however many rings there are, you add 1.5, and that's the age in years. And that's what we want to figure out. So really, if we include the number of rings in the neural network model, that's just going to predict the age easily, because it's just going to add 1.5 and it's going to figure out that that's the formula. So we're not going to use rings in the neural network model, because otherwise it's just going to be a ridiculous result, too easy. And we can just do that manually. I think it's called has a special name for this type of result, maybe a intuitive, no, it's something else. Anyways, so we're going to create the columns, and we can just do that by specifying the columns like this. We just use a list, and what I'd like to do is have lowercase names, lowercase letters for all the predicting variables, or the non-target variables, I should say. And I'm just copying this from my notes next to me, but these are just the names of the variables that was on the abalone dataset page. So visceral weight, shell weight, and rings. I'm going to make it a little bit easier to see. All right, so we've got that, and then if we, it's going to be right. Now we print df, then we've got the column names. So that's a little bit easier to read. Now we just create another column for age, and this one I'm going to capitalize because this is the target variable. This is the one we're going to predict through the neural network. And all it is just simple formula there. df is going to be the rings column plus 1.5, because that's what was set over here. Rings adding 1.5 gives the age in years. And then we look at this again, and there we go, we've got the target variable. And now what is a good habit to do is to create a pair plot using SNS Seaborn. So firstly, we can look at the info of the data frame. We can see what we have. So we have a lot of float values here. We have one object value, that's the sex, and then we have one integer value there, but that could be converted to float anyway. So the memory usage is, almost nothing, so that's fine. And then we have almost 4,200 entries. So that's a decent amount of data. Well, it's all right. So we can kind of look at this and see what we have. We could also do df.describe. And then they'll tell you the mean, standard deviation, lowest value, maximum value. What we can do is, if there's in the variables table, if there's a description that tells you what the value should range from, like maybe the minimum value, the maximum value, or the or any other information, we could look at this and see if it matches up. But there's no such information in the variables table here, so we don't have to well, there's nothing to really mash it up against, so we don't do that. Yes, okay, so that's what I'm doing here. I'm kind of like taking a look at the data and seeing what we can, now this is a simple data set, so there's not much to do here, but this is what you do in the case of a bigger data set. So we're going to create a pair plot, and the way to do that is just use Seaborn and pass in the data frame, and then we can save the figure like this, and that's just going to save it in the files, but I've already got it created here, and that's just pair plot here. Right, so this is going to give us the relationship between each of the variables. So the diagonal here is just the relationship of a variable with itself. So essentially that's just going to be, instead of a straight line, which is what the case would be if we did a scatter plot, it's a histogram. So it just shows instead the distribution of values. So we can see with the length, most of them are quite high. It's I think that's called right skewed, right, or left. I'm not sure which. Well, it's skewed nonetheless to the right, so maybe it is called right skewed. And then, you know, for something like height, the standard deviation is much lower. And then we can see the skewness or the distribution of the variables, like on the diagonal, it tells us the histogram. And we can see, I mean, this one's more normally distributed. This one is very normally distributed, the height, which is worth noting, because some functions in machine learning rely on normal distribution. I can't remember if this one does, but I'll find out as I type it out. Right, so then we have the relationship between the variables with one another. And we see we have some linear relationships between diameter and length. So there's the same variables in the x-axis in the same order. Like, I'm not going to go through all of these, but if you want, you can pause and take a look and just get, you know, for example, let's just look at an example like length and whole weight. So intuitively, if you have a higher weight as a sea, what was it, a seashell? I forgot what it was. Anyways, as an abalone or as a whatever, you probably have greater length. So it tells you that as the weight increases, the length increases, but it's not linear, which some of these other ones are more linear, like the correlation between shucked weight and whole weight is almost 1. I'm talking about the correlation coefficient there. If you don't know what that is, that's basically just a measure of the linearness of a data, or, you know, more specifically the correlation between it. So if it's a correlation coefficient of 1, then this would be, well, perfectly linear, and it's almost perfectly linear. But then something like number of rings and whole weight, you can see that as the weight increases, number of rings generally increases, but it's much higher. There's a much higher range with the greater weights. So for example, if you have a weight of 2, then the number of rings can range from like 5 through to 30 almost. And then you can see that the distribution of rings and age, it's quite similar, and that's because age is just 1.5 added to the number of rings. So the distribution between the rings and whatever variable, and then age and whatever variable, will be very, very close. What we can do from this graph is see which variables we might use for the deep learning model. And we the way we do that is see which variables there is a relation with. So for example, we're looking at the age, because that's the target variable. So we want to see which variables affect the age. And that's the last row here. or the last column, but we're going to look at the last row. So you can see that age is the y-axis here, and we can see each of the variables, how they affect the age. So generally, as the length and diameter of the abalone increases, the age is higher. Same as the height, but height has a much bigger slope. And then there's some outliers here where the abalones are really tall, but they don't have much. They're not too old compared with this group over here. Same as whole weight and shuck weight. I mean, generally it increases, but that's kind of a little bit more chaotic, all over the place. Same as all the weight variables. Shuck weight especially, this one is less obvious of its effect on age, but it still generally shows that as the weight increases, the age increases. And obviously for the rings we have a straight line, and that's just simply because rings plus 1.5 is age. So as rings increase, age will increase. They're proportional to one another. So the correlation is exactly 1. Correlation coefficient, that is. But let's get back to the code. So what do we have here? We've done the pair plots. We've looked at the data frame info. I realize I'll need to load this again because this is a separate day. So that's just for the future, so we don't need to do that. Just need to put the data in there. So that's, there we go, that's loaded. And now I just need to load in the data set again. Oops. That's the issue. Alright, we don't need to load the pair plot again because we've already got that saved. Alright, now we're going to look at the first model. But before we do, we're just going to, well, this is just going to be a brief section here, but it's going to be called setting up the data for models. We might have to add more to it, but for now, all we need to do is just create, it's called device agnostic code. And essentially it means that if we have a GPU, which is much more effective and strong way of running these PyTorch models, then it's going to use the GPU. Otherwise, we're going to use CPU. CPU. So we're going to put in this variable, this string variable called device, and it's either going to be CUDA, which is GPU, or it's going to be, and it's going to be CUDA if the torch.cuda is available. So this just tells us if it's available or not. Otherwise, it's just CPU. And this avoids the hassle of changing many sections. If for example, in the future, I want to run this using a GPU, if I didn't set it up this way, then I would have to change every section in the code to CUDA. Because if I didn't have this, then I'd just put CPU instead. I'd just put it as a string, but we can just pass in device, and whether or not CUDA is available, it'll affect what device is. But we're going to create the first model now. We might have to add a bit more here, but for now, let's just see what we need for the first model. So we're going to look at the diameter of the abalone, and we're going to see how it affects, or we're going to see if we can predict age based on diameter. We can see that there's a linear relationship here, roughly. It's not quite linear. Like if I was doing this professionally, I'd skip this portion, but just to demonstrate a simple example. We're going to use a linear model, linear PyTorch model. Just look at my notes. Yes, okay. It's the first one. And yeah, so linear. So firstly, we're going to create the x and y variables. So x is going to be the predictor variables, and then y is going to be the target variable. So y is age because we're predicting age, and x is just going to be diameter in this case. So we're going to take this from df, and we're just going to take column diameter. We're going to create a copy of this so it doesn't affect the original data frame. And then we're going to take age, and we're going to store it in y. So if we print out x, it's just going to be a data frame of just the diameter column, and then y is going to be just the age. So we're going to see if, now because this is a simple model and we're just going to do linear, we could literally just do a linear regression model instead. Using, I think sklearn has one, and there's another one as well. I can't remember the name right now, but we could just use a linear regression model, but just to demonstrate the neural network. But I'll do it this way, and we're going to get to slightly more complicated models anyways. So, okay, we're going to create a train test split, and what this does is it splits the data into training and testing sections. So usually it's the case where 20% of the data is used for testing, and then 80% of the data is used for training. And what that means is that what we pass into the deep learning model, the neural network, is training, and that's what actually trains the model. And then the way we test it to see how it performs is we use the testing data set, and it's part of the same original data set, but the reason we just separate it is because it's more likely that the model will perform well on the training data set once it's trained on that data set, right? But if it's tested on data that it hasn't even seen before, and then it performs well, then we know that it's doing what it should be doing, because we want it to perform well on data that it hasn't seen before. Right, and we imported a library before for this. This is just sklearn.model selection, this one here. Now we could just do it manually and just use slicing to slice an array and randomize it, so we can take 20% for testing, but this is a much cleaner way. And what train test split returns is it returns x train, x test, y train, y test in that exact format. So make sure you get that exact order right. And we pass in x and y and specify the test size, and then random state. This just makes it so so if you call this function again with the exact same random state, it'll give you the exact same results. Otherwise it would randomize every time, and this is just to ensure consistency. So if we get a specific train test split and then we want to see how changing the model will affect the outcome, we don't want to just get a different train test split every time. We want to get the same train test split and then actually change the model so that we see how that affects the results. This is essentially one variable in the whole deep learning process, and we want to keep that variable constant and then change something else to see how it affects. It's if you don't understand that, it's not too important. But then we just convert the x train, x test, y train, y test into tensors, and I'll show you what they look like. So if we just run train test split, and then we look at X train, it's going to be a data frame. But we want to convert it into tensors because this is what we're going to put into the model. So we first specify xtrain.values, and what that does is it just creates it into an array, and that's what we pass into tensor because the torch.tensor needs an array. So we can just copy and paste all this. Oops. So x test, y train, and y test. There we go. So now we have tensors, and this is what we can actually put into the model. I believe you can actually put in maybe arrays into the model as well, but it's just cleaner to get a tensor. It's just good practice. All right. Now for this first one, what we can do, because we only have one variable, is we can actually print. So we're going to create the model, the deep learning model later on, but right now we're just seeing what we're working with beforehand. We can get a sort of we can get a hypothesis about what we might get as a result. Now we're just going to create a linear regression model, so it's not going to be a fancy model. And if you remember from the pair plot, it was approximately linearly related, but not quite. So if we didn't have the pair plot, then we could just fixed size equals, and we could graph it separately, and this would be a good habit to get into. So we're just going to do that now, so we don't have to keep referring to the pair plot. All this is just x versus y, which is diameter versus age. Just like that. So this is exactly what we get in the pair plot, but at least now it's here so we can refer to it if we need to. Yeah, so my prediction here is that we're not going to get quite a good result because we can only get a linear regression essentially. So it's going to go somewhere in the middle. The deep learning network is going to train somewhere in the middle. So all these points on the outside, they're not going to be predicted very well, but we'll put it in here. So we're going to create the model now. So if I remember right, I imported torch.nn. Yeah, so we need these two to create the model. Well, essentially we've already used this one because we've created tensors, but then from torch import nn, that's a useful module to use. So we're going to create a linear model with a feature, one feature, and essentially it's just going to be weight times x plus bias. That's going to be the format, and I'm going to write down the format of the class. So the way I learned this is there's a video by an Australian machine learning engineer. I'm going to link it down in the comments or in the description anyways. So if you want a more detailed explanation of this deep learning method where you create the class like this, then watch that video because it's absolutely incredible. And I'd have to go into a lot of detail to match that. So I'm mostly focused on this project that I'm working on here. So definitely watch that course if you want to learn more about this process. But I'll write it down here. So a lot of this, you'll notice, well, not a lot of this, but at least the beginning of this project, you'll notice it's similar to that course, because that's where I learned how to do this, and that's what I was practicing with. It's by a man named Daniel Bork. I believe that's how to pronounce it, but I'll link it down. Okay, and then there's this. We don't need to do that. So this is literally just a linear regression model, essentially. We've got weights, or AX plus B, pretty much. And what this does is it initializes over here, and it'll create the weights and create the bias using random numbers, essentially, and we're just creating one over here. It requires grad is there so that back propagation can work properly. If I'll link a good series on gradient descent and back propagation in the comments as well, if you're interested to learn more, because again, that will take a long time to describe this here, but definitely watch that if you're interested to learn more about the theory. And then the forward function is essentially the bulk of the model. So it's what's going on, and what's going on here is just we're multiplying weights times x plus bias, which is a linear regression model. So that'll be the model, and then what do we do next? All right, we're going to actually create an instance of the model, and then we can create the training loop, which will actually train the model. So this is model 1, and we're going to specify 2 device. So this just specifies whatever device we're using. So since we're using CPU, that's the one that's going to go to. And this is essentially the method that we used before, where we were specifying the random state. So manual seed is the same as random state. It means the same thing. So that way we're not going to get a different result from the model. It's going to be the same every time we run it. Device is not defined. Now it's going to be defined. Okay, so now we have the model. Okay, so next is the training loop. We've got, we're going to do this manually. I believe later on we'll create a function if I don't talk too much beforehand, if we have some time. But we're going to specify the loss function and the optimizer first. So loss function, we're going to use L1 loss. That's a pretty standard loss to use for these sort of situations. And then stochastic gradient descent. And then we're going to specify the learning rate as well, which is how fast the model trains. Okay, and then we need to specify how many times we're going to train the model, which is just the number of epochs. We're going to create some lists as well. I'm just going to call them lists and then what they are. And this is where we're going to put in our what we get from the model, the training loss and the testing loss, and the number of epochs, because we can use this to graph later on and also to just print the results as they come. This is just going to be for visualization and recording purposes. Okay, and then we create the for loop, and we're going to loop over the number of epochs, and this is the format for the for loop. I'll explain this briefly after I write it down. Okay, so this is the training, well, the first section of the training loop. Well, it is the training loop. We also got a testing, kind of a testing loop. We'll write that in a sec. But this just puts it into training mode, the model. And remember, the model was the instance of the class that we created. And then we're seeing how the model predicts the training predictions. So we're just passing in X train into the model and seeing how it does first up. Now, first up it's going to do pretty badly because it's just, it hasn't really been, well, it hasn't been trained at all yet, so it's just random values. And then it's got the training loss, which is how badly the model does. So we're putting the training predictions and then Y train into it, and it's going to compare the two and see how well it did. Zero grad, that makes sure that the gradient doesn't keep. So with every calculation, the gradient gets calculated as per back propagation. But then due to memory saving issues, PyTorch keeps adding gradients to it, essentially, to the loop. So you have to zero the gradients with every iteration, otherwise the gradients aren't going to be calculated properly. And then this is back propagation there, and then optimizer.step, so that just optimizes the, that just trains the model as per the gradient. So it'll, essentially this is stochastic gradient descent over here, because we created, that's our optimizer, it's stochastic gradient descent. So whatever optimizer we use, it's going to do that. And that's this is, I mean, all of this is preparation, but this is really what trains the model. This is what makes it closer, makes the model get closer to what we want. Okay, and now we do evaluation mode. So this is the testing loop that I was talking about earlier. So eval, and torch.inference mode, that's going to be another data saving habit to get into. So this does not calculate the gradient. So we don't want to calculate the gradient when we evaluate our model on the testing data. So that's what torch.inference mode does. There's also torch.zero grad, but inference mode is more up to date, or at least more used. So all we do is then pass in X test and see how it does on the testing. So over here we passed in X train, here we're passing in X test, and remember X test and X train, they are separated, so they're not, they're part of the original data set, but we separated them earlier, so the model does not see X test when it trains. It only sees X tests over here when it evaluates. That's what we want. And then we calculate the loss, which I'm going to call test loss, and this is just going to be the how badly the model does in evaluation mode. And then that's essentially the loop, but we need to print something. So what this first section does here is it just says with every 10th epoch, so modulus 10, it's going to be multiples of 10 that make this equation equal to 0. So we're going to, this is going to be for graphing purposes, where we append the epoch, the training loop, and the training loss and the testing loss to the lists. So we're going to do the same thing for train loss, but we need to detach the loss and then do dot numpy. What I'll do is I'll just comment this out and then I'll run this and you'll see why we need to do that. So I'm running this for 1,000 epochs. Hopefully it doesn't take too long. Well, it's still in the optimizer section. Okay. Oh, it's missing the forward function. That's just because I indented it too much. So what it said is it's missing a forward function, but you know, you might be confused because we already wrote this, and there was a forward function, but we just indented it wrong. So it was under the initialization function. So we just need to indent it backwards like this. And then if we run it again, run the model again, and then do this. Yeah, that was quick. All right. So if we look at train loss here, you can see it's a tensor, but we can't store that into a list. So we detach first, and that detaches the gradient. So we have the grad function here, and that indicates that it's recording the gradient. So we detach it, and then we just convert it to numpy. And that's what we're going to store in the list. So, oops, what's happening here? Like that. Yes, good. And then we're going to do the same thing for testing loss. There we go. And then we're going to print out the result, which is just going to be the epoch, because we're going to print out what we're interested in. And we're interested in how the training loss and the testing loss goes down, but we're also going to record the epoch. We don't need to put this here. There we go. So this is just going to print out every 10th iteration. So if we run this, we should really reset it, because otherwise it would run on what's previously ran, and that's not the beginning. So you can see that we begin with epoch 0, training loss is 12.7, and it goes down to 12 point something else. It goes down to 11.8, 11.7. But I think that that's a really messy way to record things with text. So instead, we're going to actually use the model again to predict on testing data, but once we finish the entire epoch loop. And we're going to visualize it in this case. So firstly, we just need to run the model on testing data again, and this is going to be the model that's that we already trained through the large number of epochs. So let me write all this. Okay. So what we're going to do here is we're going to create a set of axes, and one of them is going to be simply a scatter plot of x test and y test, which is what the true values are. And then we're going to do the scatter plot of x test and y preds, which is what the predicted values are. And then in the second axis, we're going to go with the number of epochs and the test loss. So we're going to see how the test loss goes down, which is essentially what we're concerned with more. I mean, it's also nice to see the training loss go down, because then at least you know that you coded up the model format correctly, because essentially the point of the model is to get the training loss down, but the testing loss just comes down indirectly. So testing loss is what we're concerned with but training loss is what we're actually affecting with the model. So you can see that, well, the test loss does go down. It goes down actually linearly, which is interesting. But the prediction is pretty bad. You can see that the data is up here and then the prediction is down here. Now we expected that the prediction wouldn't predict the data perfectly, but we would hope it's somewhere in the middle, you know, rather than at the bottom there. So the way I'm going to fix this is I'm just going to reset the model. We're going to write the learning rate as higher. So we're going to put the learning rate high, which means that the model learns faster. Just get rid of this because that's annoying. And then let's run it again, see how it goes. So that's a little bit better. But if we run it again, maybe we can get it even better. So I'm going to run the training loop again and then visualize it again. So yeah, you can see it's kind of going a little bit, it's asymptotic here, but I don't think that it changed too much. I'm going to increase the learning rate just a little bit more and see if that does anything. And again, with each cell run here, I'm running for 1,000 epochs. So it's still going down, but the prediction isn't really changing much. So it looks like it's found a point where the loss is minimized. And that's probably because there's less data points up here and there's more data points down here. So that's why it's biased towards this section over here rather than in the middle. So I'm guessing that's why that's the case. So let's just run it a couple times. Yeah, it's about, I mean, the test loss is going down. We could really just run it for like 10,000 and see if that does anything exciting. But it looks like it's found its happy place. I don't think it's going to move too much based on the previous examples. Okay, maybe it has. It looks like it has gone down a little bit, but it's still biased towards this bottom section here, and that's probably because there's just more points there. Well, there are definitely more points compared to this top section here. There are more points at the bottom. If you run it too much, it might be might go in a different way, but we'll see. Yeah, so now that we've run it too much, we see that the test loss is all over the place. And this is, I mean, even if the test loss goes down, I don't remember what the values were before. I don't know if this is lower than it was before, but even if it does, I don't really like seeing these sort of test loss curves because they're pretty chaotic. And remember, this is every 10th epoch, so it could be the case that the test loss is super high and then super low and then super high, you know, something crazy between those 10 epochs. But the prediction is as good as we really expected, so you know, that's the best that we could achieve here. So really that's the format. So you create a model and then you visualize the results and then you see, and then you kind of interpret the results. See if it makes sense, the results that you achieved. Now we're going to do the same thing, but with another model. So luckily we can copy a lot of our previous code. So we're just going to create model 2 here, and that's going to be diameter and whole weight. So whole weight was this one here. Diameter, we're not going to do diameter and length because those two are related by themselves. Like you can see diameter here, and then length is on the x-axis. These are very closely correlated. So there's no point in putting them together. But diameter and whole weight, for example, which is over here, you can see that it's correlated, but not linearly, not too linearly correlated. So that's a little bit better to use, especially since we're using a linear model. We're pretty much using a linear regression, just a fancier one. We could also do diameter and, oh no, we couldn't do rings because rings is basically the target variable, or it is just minus 1.5. Okay. So what are we doing next? So we've got the, I'm just gonna, can I copy both of these? I can. So we're going to do the same format. We're going to create X and Y, but in this situation, we've just got diameter and whole weight. Y is the same, Y is age. Train test split is also the same. But we can create a 3D plot now. So let me pause it and I'll... Okay, so this is just going to be a 3D plot of diameter and whole weight versus Y. So we don't have that in the pair plot, so this is going to be new. We have the separate points. We have age versus diameter and age versus whole weight. But we don't have them combined into a 3D plot. And that's what this is: X, diameter, X, whole weight, and Y. And what's happening here? We need a 2D list, don't we? Yeah. There we go. So combining combining diameter and the whole weight on the X and Y axes, and then age on the Z axis. You can't see the rest of this, but that doesn't matter. You can see that it is related. They are definitely related, which makes sense. We're getting more complex information here because it's a 3D plot, so it's harder to tell what's happening. But it is still nice to know that they're related, so we can see if we can create a model that works with that. So in this case, I'm going to specify the number of features just to put into the model, so we can just run this separately. So there's 2 features. Okay, now when we do the code for the class, this one is going to include 2 different features in the input, because we've got a number of features too. But since we specified that in a variable, then it won't be too difficult to implement. So I'm going to write down the code first and then I'll explain it afterwards. Okay, so we've got the code here. You can see the main difference between the previous one and this one is that the previous one, we actually created the model manually. So we did weights times X plus bias, and we used the dot parameter there. But this one, we just put nn.linear, which is going to create the linear regression or the linear type model automatically. So it's going to set the parameters automatically. So that's why we just put in the forward method here, we put layer 2 of layer 1 of X, and in the previous one we didn't do it like that. We put weights times X plus bias. So this is where we put the manual formula, but then this one, the linear layers just do that automatically. So the in features here, this is the number of features, which is 2. So it's going to take in 2 and it's going to put out 16, and then the second layer is going to take in 16, which is what the first layer puts out, so those have to match. And then the out features is going to be 1. And then this 1, hopefully we're going to get equal to the age. So now we just have to create the instance. So it's going to be pretty similar to the previous one. In the process anyways. So we're going to use manual seed of 10 again, and then we're going to create the instance. I'm going to put it to the device, which is going to be the CPU in our case, because we're not running this with a GPU. So we run this. Well, I'm not sure if I run run this one. Let's just run these again. There we go. And now we do the training loop again. So we're going to use the same optimizer and the same loss, which is L1 loss and SGD. And these are pretty basic ones. So they work with these basic linear models. So we can literally just copy and paste it. Now, depending on how much time I've gone through with this video, I might functionize it, which is what I did in the when I was just coding this by myself. And I created new files for the classes, for these classes, the models, but it depends on how much time. Let me just see if I need to do anything. I don't think I need to change anything here. Let's just put it for a lower epoch. Oh yeah, we need to do model 2. So this time it's model 2.parameters. Model 2.train. There we go. And model 2 there. And that'll be everything. Now, once we train it, then we need to visualize it in some way. So we can what we'll do actually is I'm going to code this out because it looks slightly different than the previous one. So I'll code it out and then I'll come back to the video. All right. So this is going to be the visualization section. So if we run the training loop, then I'll show you what the visualization section is. What would we have here? Train parets equals x train. I believe the issue with this where is it? Here it is. All right, so firstly, I've just noticed that we need to put the X train and Y train to the devices. That's not the reason that we got the error, but I'll put that there first. And the tests. So this is just good practice. And the reason that we got this is because when we have two features, there's an issue with the dimensions when we pass it into the model. And the way to fix that is to, well, firstly to change it to float, because there's also an issue with the type as well. So it says they must have the same D type. We've got double and float, so we're going to convert the double into a float. Now the double was X train, and well, float and double, they mean the same thing, but I believe it's just a difference between PyTorch and PyTorch's tensors and then just normal Python. Because we converted them to tensors earlier on over here, but I don't believe it converted the D type correctly. I'm pretty sure that's why this issue comes up. And then dot squeeze to get the dimensions right. And we need to do that the same over here with xtest. That's model 1 is not defined. Oh yeah, because it's model 2. So I did forget to put that one there. There we go. Now it's run. Now, as long as nothing's wrong with this one, L epochs, because I copied and pasted this from before. It's list epochs. That's it. Test loss. Okay, there we go. So we have the test loss curve, which well, because of the difference, because of this here, we've specified that every 10 epochs we record a value, and that's why it kind of drops down suddenly. If we include those values from in between, we would get a more steadier drop rather than a drastic one. But this model prediction of testing data, this is more important to me to look at how the model does. We have the data, which is translucent in blue, transparent, slightly transparent, and then our prediction is the red one. So we can see it follows the trend generally, but obviously it's not going to predict these values outside of the middle there. Now this is it looks like it's better than the previous one, because we have those two features, we get more information about the data, and that can be used to predict the age a little bit better. Okay, I'm going to kind of go through this a little bit faster because I've realized how long the videos have been going that I'm recording for. So let's go for the third model. Actually, in fact, I'm going to copy all the code from my notes file here, and then I'll get back to the video afterwards, and then I'll explain it as we go. That'll be a lot better than me writing it down every time. So what I've done is, when I was coding this before, I actually created separate files for the models. I'm going to do that with model 4 and 5. So model 3, which we haven't done yet, well, I haven't just shown you yet, that one's going to be just in this file here. But then model 4 and 5 are going to be imported separately, and then we're going to do the same with the training loop. So if I just run this, and I'll show you the training loop. So this is just a class version of the training loop and a functionized version of the training loop. So we have the epochs, the train loss, and test loss initialized at the beginning, and then well, I mean, essentially it's just the training loop. So we have the recording frequency that's going to be used later on here, and that's going to record it as usual in the training. So it's going to record the list of epochs, train loss, and test loss, and then it runs for a certain number of epochs that's going to be specified in the parameters here. It just goes through the training process there, and then the evaluation process. And then we have another method where we can print the results, which is going to print the epoch, the train loss, and the test loss. And then visualize prediction is also in this class as well, and it uses those from earlier to visualize. So it's got various plots. One of them is the absolute errors between the predictions and target. That's going to be a useful one. And then absolute errors per data point prediction. And then we have the train loss and test loss curves. But we'll see that over here as well. So we're going to continue with model 3, and here we go. So model 3 is going to be similar to model 2, but it's just going to include viscera weight as well. So if we look at viscera weight and whole weight, we can see that, well, I'm going to guess that they're quite correlated. Viscera weight, where's whole weight? Here, viscera weight and whole weight. So they are very linearly correlated. So we might expect that it won't add too much to the model, but I'm going to do it anyways just for completeness. Just then we can see, well, we won't be able to actually visualize it as we did before, because we can't create a 40 plot like this. But this is where we start to create these different sort of visualization graphs. So we have the histogram of absolute errors between the predictions and target, so we can see how well it does with that. Splits the data into training and testing. Number of features is 3, and this is the model, which is just it takes in 3 features, puts out 32, and then does the same thing. and then puts out 1 in the end. So this is very similar to the model before. And if we run, and this is the training loop here, pretty exactly the same as before, except I've just changed the variables around a little bit, the name of the variables. So I'm just doing L underscore epochs for the list. But yeah, essentially the training loop. And then visualization section here. So we predict, or we get the predictions using evaluation mode. And then we create all these plots here. So we run this. We get, train loss curve and test loss curve. I'm actually not too interested in them because, I mean, as long as they're going down, I'm happy with that. But then these ones are some graphs that I found actually pretty useful. I was playing around with different ways to visualize it. So this left one here is just the absolute errors between the predictions and the target. And you can see that most of the errors are down between 0 and 1 or 0 and 1.5. So yeah, most of the predictions are down below on the in this section here, and that's useful because that means that the error is small for most of them. We have some that are quite large here that you've got a greater than 12 absolute error, but that's expected, but that's just a small amount. And this graph here on the right hand side, this is per data point. So we have about maybe 850 data points, and you can see that the x-axis ranges from 0 to 850 or whatever this number is, and that explains each data point what is the actual absolute error. So most of the data points, most of the points on this graph are centered down below here, which is expected. That's the lower absolute errors, and that corresponds to this start of the histogram here, this section here. And then we have a few, well, not a few, we have some data points up high here, and that corresponds to this section of the histogram. So essentially, if we get a good model, we want it to bring most of the absolute errors to the left. So it should be more left skewed. The more left skewed it is, the better. In fact, if we get all the points in the 0 section, 0 to 1, that'd be perfect, or almost perfect actually. And then as this absolute errors per data point prediction graph changes so that these points here at the top get more grouped together at the bottom. So the more points that are grouped together at the bottom, the better. That's how we look at the model. So if we run the training loop again, let's just run it a few times. You can see, just take a look at the data now at the graph, and then if we run it again, we can see how it changes. It's kind of hard to visualize actually as it changed. I don't think it changed too much. We can see that the train loss and test loss curves are still going down, but I think that this point here did change. There's more absolute errors on this first bar here in the histogram, so that's good. We want more absolute errors that are small compared to large. Now the next model is still going to use diameter, whole weight, and viscera weight. But what it is going to do is, first of all, it's going to use the imports from before. So we actually create the instance of training loop, so we don't have to write it every time, and it's cleaner. We use L1 loss SGD, and after putting the data to device, specify 10,000 epochs. That's a pretty good amount of epochs, so we can see how well the model does with that. We train it. So if you look at the training loop here, it needs model, loss function optimizer, epochs, and then all the data. And that's what we put in here. So we won't worry about printing the results, but we will visualize prediction at the end. Now over here is where we create the instance of the model. So model 4, I've created here as a separate class. The difference is, well, one, we've increased the hidden layers, or the number of neurons in the hidden layers, I should say. So from 32 to 64, we've increased that. We've kept the number of layers to 3. And I've also changed the way that this is set out here. So if we look at before, here, I've returned in this format here, which is layer 3 of layer 2 of layer 1 of X. Here I've just made it a little bit cleaner. I like it in this method. You don't have to do it in this way, but I like it like this. It looks nicer. So firstly we do layer 1, and then we activate 1, then layer 2, activate 2, layer 3. And the activation functions here, they're a method to non-linearize. Is that a word? Non-linearize? Maybe. But to make the models a little bit more advanced. So p-relu. So this is what p-relu is. I forgot what the p stands for in it, but it doesn't really matter at this point. So relu would just be 0 if so if x is less than or equal to 0, then x would be 0, or y would be 0. And then if x is greater than or equal to 0, it would be x. So it would be linear. So relu would look like this, but it would have a straight line here as 0. And the issue with that is that the gradient there is 0 for all those points less than or equal to 0. So that can cause a vanishing gradient problem, which, well, I mean, when you're doing the backpropagation and calculating the gradients, if one of those gradients is 0, then that can multiply with the other factors in the formula. So p-relu is a fix for that, essentially. Now, obviously, if x is equal to 0, that causes an issue as well, because the gradient here can't be calculated. But now it fixes it for the case if x is less than or equal to 0. So the slope here is small, but it's still existent there, so that won't cause as much of an issue. So that's the activation function I'm going to use. And that will make some non-linearity in the model. Yeah, so we can run this, and it will train for 10,000 epochs, so it should take a little bit, but not too long. Okay, so that did actually take a little bit, but pause it for you. Yeah, so you can see that this is the histogram of absolute errors, and then this is the absolute error per data point prediction. Now, if we look at before, actually looks quite similar. Let's bring this up so we can see. So it is actually very similar. So you can see that using the non-linearity didn't really help too much. It's actually very, very close. It's not exact, which is good. I can tell it's not exact because these 2 points are different. So I'm sure other ones are different as well. But that's very close. So that didn't help too much. But something that might help, and I actually don't remember if it helped, but we'll find out, is using tan-h. So this is another activation function. Tan-h. So this is the formula here, and this is what the activation function looks like. If x is quite negative, then it's an asymptote over here to this value, which is -1. Otherwise, it's 1 as x gets quite positive, and then in between it just kind of joins up. So this is an interesting one that I saw, so I wanted to see how it works in the code. And then in Model 5, so the only difference is that we've just swapped the p-ReLU along with 10H. So we're still using the same features, diameter, whole weight, and visceral weight. And we're actually using the same number of neurons as well, 64. And yeah, the only difference is just these activation functions, which are 10H in this case. So this first section is creating X and Y, splitting the data into train and test, creating the instance of the model, which is model 5, and then we're just running the training loop with L1 loss and SGD. So with this, what I'm going to do actually is just put the learning rate at 0.001, just so it's consistent with the previous one. And then we can see, and then we can truly compare the two. Actually, that might be an issue with what I did before. So before, when I was comparing the two, I had different learning rates. Interesting. Well, anyways, I won't worry about that now. But we'll run this last section here. So this one looks quite different, we can see. Now it is a good sign to see that the training loss and the testing loss, the curves look similar. Because remember, the model hasn't seen the testing data. So the fact that these are similar shows that the model is training on the training data, but works on data that hasn't seen, and works in a similar sort of fashion. Now the histogram here, actually I think this did a little bit worse, because we can see that with the previous histogram, most of the data was in this first bar here. And then with this second one, we've got a lot of data in the second bar. Now, the combined amount of data here in the first and second bar looks to be about, well, what's that? This one's about 210. This one's about 200 and, let's say 220, so that's 430. Here it's 260 plus 200, which is 460, right? So this first one did better. p-ReLU did better. Because this means that there's less data points in this first two bars, so more data points are in the later parts as well, and we can see that these outliers here, or the data on the right hand side, the histograms are slightly higher, the bar is slightly higher. Here they're lower. So what I would get from this analysis is I would say that maybe we don't pursue the 10H, and maybe we play around with the p-ReLU, because let's say we run it for more epochs, or we maybe change the number of neurons in the hidden layers, or maybe add more linear layers. Maybe it would work better. And we're already coming from a starting point where it's doing better than the Model 5. So if we run Model 4 again, and then we run it for more epochs, so let's put a learning rate as something higher as well, and then we'll run it for 1,000 more epochs. So just see if we can remember what this looks like now. Let me run it again. Oh, have I reset it? No, I haven't reset it. I thought I reset the model, but I put the model instance in the previous one. Well, the train loss and test loss curves are going down, which is a good sign. But I don't think they're going down by a significant amount, because this is about the same as before. Actually, no, that is about the same as before. Yeah, maybe slightly more in the first bar, which is good. But it's not so the model predicts generally pretty well with with low errors, but it's not too good. So I'd probably try different models in this case. Or maybe I'll put the learning rate something pretty high, and maybe that'll do something. No, that made it do worse. Yeah, and you can see that the train loss and test loss curves are not what they should be. And the reason for that is that the learning rate is high, so we're obviously getting quite close to the optimum amount for that model. And when the learning rate is high, then that can cause instability in the curves. And you can see that this first bar is now less than 250. Before it was more than 250. And there's less points total in this section. Some of these bars here are also higher than before. But that is an analysis of abalones using simple deep learning models. If you have any questions or comments, please write them down. Thanks for watching.